me make a very short introduction to John. So John is a Clerk Maxwell Professor of Theoretical Physics at King's College, London. His research, I would say, relates directly with experiments. So he has been studying how to interpret measurements, how to interpret experiments, and how would be physics at future colliders. And he made very important contributions to the field of particle physics and also astroparticle physics. And in particular, he was really, he played a very important role in the early days, since the early days in which the Higgs discovery was one of the main goals at the LHC. In fact, he wrote, together with Mary Kay Gaillard and Anopoulos in 1976, a very important paper, which was in fact mentioned by Marumi, where they laid out, they sketched a phenomenological portrait of the Higgs boson. And this paper was very influential. Just to put things into context, in 76, 76 was just 3 years after the Gargamel experiment, where the neutral currents were discovered. And it was before the discovery of the W and the Z bosons. So this was really an important work which came very early. Then, of course, John made important contributions in other fronts, grand unification, CP violation in kaon decays, and also and especially work on supersymmetry, where he pointed out that the lightest supersympathetic particle can be a dark matter candidate. And then also he computed the radiative corrections to the mass of the Higgs in the MSSM, and this was also very, very important. And let me just mention also that John played a very important role during this ECFA workshop in Lausanne in 1984, where the physics of the LHC was taught and decisions for the LHC were taken. So I'm very happy to give the stage to John. His talk, his title is Theoretical Path to the Higgs Boson Discovery. Please.
Now you can see, our vision as theorists, that we often have some idea that there may be some peak off there in the distance, and we set off across the desert of theoretical calculation and experimental effort to try to see whether that vision is reality. And of course, in the case of the boson, it turned out to be real. Next slide, please. So I'd like to start the story back in 1957, when this famous paper by Bardeen, Cooper, and Schrieffer proposed a theory of superconductivity. Of course, superconductivity had been known for decades. And it was thought to be due to the condensation of pairs of electrons, so-called Cooper pairs. And Bardeen, Cooper, and Schrieffer showed how that pairing of electrons could be caused by phonon interactions. That meant that in a superconductor, the lowest energy state would have a non-zero charge density. It would break, apparently, the U1 of electromagnetism. Now, probably a better word than break is hide, because the underlying theory actually does have the original U1 gauge symmetry. It's just that it's not manifest in the spectrum of the theory. Next slide, please.
I'm trying to do it, but it's not working. It's freezed. I don't know. If no, sorry. Let me stop share and try again. Okay. I'm sorry, but I don't know why. Sure. Okay.
Okay. So Nambu and Phil Anderson gave an interpretation of this phenomenon of superconductivity in terms of the spontaneous breaking, so-called gauge symmetry, although I repeat again, a better way of talking about it is as a hidden symmetry. And they showed explicitly how the photon acquires an effective mass in a superconducting medium, at least in a non-relativistic theory. Of course, they were dealing with a non-relativistic situation. Next slide, please. Now, these ideas of spontaneous symmetry breaking or hidden symmetry were actually introduced into particle physics by Nambu in 1960, when he proposed his theory of chiral symmetry breaking, in which the pion would play the role of being an approximate Nambu-Milestone boson of an underlying chiral symmetry of the strong interactions. Now, this is not a local, sorry, could we just stay with the previous slide for a second? At this stage, we're talking about a global symmetry. We're not talking about a local gauge symmetry. And there was quite a lot of discussion in the literature as to whether one could extend the previous papers to a local Lorentz invariant symmetry. Next slide, please. So these were the people who actually succeeded in doing that. So on the right there, we have Robert Brout, who unfortunately passed away shortly before the Higgs boson was discovered. Next to him, we have Francois Englert, who was at the discovery event in 2012, and of course shared the Nobel Prize with Peter Higgs, who's in the inset. And you also see, going from left to right, Tom Kibble, Graunik, and Hagen, who also wrote a paper on how you could spontaneously break a gauge symmetry in Lorentz invariant theories. They wrote their paper a little bit after the papers by Englert, Brout, and Higgs, as I'll mention in a moment. Next slide, please. So these are the titles of the papers by Englert and Brout, and actually two papers by Peter Higgs. So chronologically, the first one was the one by Englert and Brout. Peter Higgs' papers appeared a few weeks later, but they were space-like separated in the sense that back in those days, communication wasn't instantaneous like it is now with the preprint archive, and news of their work had not reached him when he wrote his two papers. On the other hand, Graunik, Hagen, and Kibble were aware of the previous papers when they published theirs a couple of months later. And I'd like to give a shout out to Migdal and Polyakov, two extremely well-known theorists, of course. But when they were only about 21 years old, working in Russia, not knowing anything at all about this work in the West, they came up with the whole package of spontaneous symmetry breaking, actually even including the non-abelian case. And their paper was delayed for quite some time for publication by the senior members of the academy, who could not believe that two young students could do something so remarkable. I checked the other day, and Peter Higgs's paper had just 5 citations before 1967. 1967, of course, being the year when Steve Weinberg wrote his paper that I'll come back to in a moment. So next slide, please. So about 10 years ago at King's College London, we had a talk by Peter Higgs. Peter Higgs, of course, was an alumnus of King's. And he took us through some of his thought processes in developing his theory. And you can see here on the left-hand side, he quotes Phil Anderson as saying that he thought that it should be possible to do spontaneous symmetry breaking of a gauge symmetry in Lorentz invariant theory. But other people were more skeptical, and in particular Gilbert in June 1964, wrote a paper saying, no, it's not possible. And Peter Higgs read his paper, and he realized that there was a loophole in Gilbert's argument. So he sent his paper to be published, and it was accepted immediately. But at that stage, he didn't have an explicit model. A week later, he had an explicit model, and he sent that for publication, but that was rejected. So he was somewhat surprised, but he sent it to another journal, and his referee suggested that maybe he'd be a bit more explicit about the physical consequences of his theory, and that paper was accepted, and that's the paper where the existence of the Higgs boson is explicitly mentioned. So the other founding fathers have told me that they were aware of the existence of this boson, but they didn't comment on it in their papers. And that's why I guess we've come to call it the Higgs boson. Next slide, please. So that picture that I showed you a couple of slides back was taken in around 1965 when Peter Higgs was at Chapel Hill in the US, actually working on a follow-up paper. And this is actually quite remarkable because he goes into a lot of the phenomenology, which is of direct relevance to the LHC. So, for example, he discusses the decay of his boson into pairs of vector bosons, and he discusses vector boson fusion and scattering and so on. So that was, as I said, quite a remarkable paper. Next slide, please. I would also like to mention this paper that appeared in 1966 by Tom Kibble. So the previous work back in 1964 had all been in the context of an abelian U1 gauge theory, and apart from the paper by Migdal and Polyakov. And Kibble, who was unaware of their work, wrote the first Western paper on spontaneous symmetry breaking in non-abelian gauge theories. And in fact, he explicitly asked the case of a U2 theory. So very much like SU2 cross U1. Next slide, please.
Again. Sorry. Stop share. I don't know why. Here we are.
Okay.
Sorry for that.
No problem. So now we arrive in 1967. And that was the year when both Weinberg and Salam proposed including the Englert-Brout-Higgs mechanism in what we now call the standard model. But the most complete and lucid description of this is this paper by Steve Weinberg, a model of leptons. A model of leptons because he didn't discuss quarks. He didn't discuss the strong interacting sector at all in this paper. But he had the electroweak sector of the standard model. He had SU2 cross U1. He had the mixing of the Z and the photon. He had neutral currents. And he had Higgs lepton couplings. In fact, there's explicitly an unnumbered equation, which you can see in the left column of his paper, where he gives the coupling of the Higgs boson to the electron. So we haven't seen that yet, but we have seen the corresponding coupling of the Higgs to the muon. He actually comments that that would be much larger than the coupling to the electron. So this paper, I checked the other day, had 2 citations before 1971. 1971, of course, being when 't Hooft and Veltman proved that spontaneously broken gauge theories were normalizable and then sensible theories to consider. Next slide, please. So already at this stage, we had the most important couplings of the Higgs boson, the classical couplings. Higgs had discussed the coupling of the Higgs to 2 vector bosons, and Weinberg had discussed the coupling of the Higgs to 2 fermions. So this laid the basis already for much of the beautiful experimental results that Mumumi has just discussed. Next slide, please. So as I mentioned, there was very little interest in these ideas in the theoretical community until 't Hooft and Veltman proved that spontaneously broken gauge theories were renormalizable. Of course, in 1973, Kobayashi and Mascara extended the theory to 6 quarks and showed how one could include CP violation. It's already been mentioned that neutral currents were discovered in 1973, so the first experimental confirmation of a standard model prediction. Then the J psi was discovered in 1974, and the tau lepton in 1975. Next slide. So this, as Mumumi has already mentioned, was the context in which Mary Gaillard, Dimitri Nanopoulos, and I wrote our phenomenological profile of the Higgs boson. So at that stage, the gray-haired old professors sitting in the front row of the seminar still regarded these ideas as being pretty speculative and hypothetical. And we didn't know what the mass of the Higgs boson might be, and maybe the standard model was not right, and so on and so forth. And so all those factors contributed to us writing at the end of our paper that we don't want to encourage big experimental searches for the Higgs boson, but we do feel that people doing experiments that might produce it should know how it would show up. So an infamous piece of advice, which was fortunately not followed by the experimental and accelerator communities. Next slide, please. So one of the things that we calculated in that paper was the decay of the Higgs into 2 photons, which is a coupling that's not present classically in the standard model Lagrangian, but it is generated by loop diagrams. At that stage, no heavy quarks were known, so we just calculated the contribution of the W boson, diagrams you see there on the left-hand side. And okay, we were, I guess, particularly gratified to see that Higgs into gamma gamma was one of the discovery modes at the LHC. And of course, the fact that you see Higgs go to gamma gamma told you immediately that it was not a spin 1 particle, a boson, but not spin 1. So it immediately told you that this is a unique particle. So one of the other things that we discussed in that paper was the production of the Higgs boson in association with heavy particles such as the Z boson, which was, of course, the favored search pattern at LEP, and has also now been observed at the LHC. Next slide, please. So I'd like to mention 2 other key papers that appeared a couple of years later. One was this paper by Georgi, Glasha, Maciejek, and Nanopoulos, where they discussed 2-gluon annihilation to produce a Higgs boson, which of course is the dominant mechanism for producing the Higgs at the LHC, which we hadn't calculated back in 1975 because no heavy quarks were yet known. But they show that heavy quark loops could generate an interesting cross-section. And they also extended the discussion of associated production of Higgs bosons and Z particles to hadron colliders. Next slide, please. So I think it's fair to say that looking for the Higgs was not top of the experimental agenda at this stage. Top of the agenda was definitely to look for and discover the W and the Z. And of course, teams at CERN using the CERN P-bar-P collider, led by Carlo Rubbia, discovered the W and the Z. And that discovery immediately moved the Higgs boson up the experimental agenda. As I comment here, the top quark was at that stage still undiscovered, despite certain claims at the P-bar-P collider. Next slide, please. So the greater perceived importance of looking for the Higgs boson was a very important feature of this paper by Eichten, Hinchliffe, Lane, and Quigg, which discussed the new physics that one might look for at the superconducting supercollider, the SSC. So this is the front page of a review paper that they wrote in 1984, setting out the physics case for the SSC. Next slide, please. So in parallel to their paper, as was already mentioned, there was an ECFA workshop on the physics program for the LHC held at Lausanne at CERN. And together with Graciela Gelmini and Henry Kowalski, we got the job of assessing the various different types of new physics that one might look for. And of course, pride of place went to the production of the Higgs boson. And here are a couple of the processes that we considered in our paper, gluon fusion and WW fusion. Next slide, please. So the next paper that I would like to mention is one that was already highlighted by Marumi, namely the Higgs Hunter's Guide, which first appeared in 1989. And this was a very comprehensive study of the Higgs boson, much more comprehensive than what we had done back in 1975. And it set out in great detail the prospects for Higgs studies at the SSC and also other high energy proton-proton colliders. Next slide, please. So maybe we just pause for a moment here. So we've got the standard model, which, as I mentioned, was ignored for several years. But there had been, of course, various confirmations of the standard model in the late 1980s. The fifth quark had been discovered, charm, of course, had been discovered, neutral currents had been measured with quite high accuracy. But I think the real glory days of the standard model came with high precision tests at LEP and also the SLC at Stanford. And if you look at the first two lines of the standard model Lagrangian, those two lines were studied with high precision at LEP and the SLC. But the two lower lines, where you see the Euclid interactions and the Higgs potential, there was basically no direct evidence until 2012. Next slide, please. So, as I mentioned earlier on, we didn't know initially what the mass of the Higgs might be, or for that matter, what the mass of the top quark might be. They were not predicted from first theoretical principles. But Tine Veltman pointed out that high precision electroweak measurements are sensitive to quantum corrections. For example, to the top quark was a quadratic sensitivity. The sensitivity to the Higgs mass is logarithmic at the one loop order. There's a quadratic dependence at higher orders, but the leading dependence is only logarithmic. And you see at the bottom of the slide the way in which these heavy particles contribute to delta rho, which is related to the WZ mass ratio that we discussed earlier on. So sensitivity to the top quark is much larger than that to the Higgs boson. But precision electroweak measurements gave us some first hints, not just of the top quark mass, but also about the Higgs mass, as shown on the following slide. Next slide, please. So in 1990 and 91, together with Gianluigi Fogli and his student Eligio Lisi, we made the first attempts to estimate what the Higgs mass might be based on precision electroweak measurements. And so, of course, these were extremely inaccurate, and you could argue, well, they don't exclude anything. On the other hand, incredibly early, it was already a very, very slight favoring of a relatively light Higgs boson, even before the discovery of the top quark. But that tendency, of course, became greatly strengthened after the discovery of the top quark at Fermilab in 1995, which enabled these calculations to be firmed up considerably. Next slide. At more or less the same time, as Marumi also mentioned, groups of us calculated the radiative corrections to the Higgs mass in supersymmetric models, taking into account the possibility, the probability that the top quark was rather heavy. And I sometimes refer to this as the most expensive calculation that I've ever done, because before calculating these corrections, it looked like the lightest supersymmetric Higgs boson would be within reach of LEP2. But these radiative corrections could push it up beyond LEP2. It could, for example, be 125 GeV, in which case you would need the LHC at a cost of a few billion Swiss francs. Next slide. So this picture from the GFITR collaboration, Marumi has already shown you, and it nicely combines the information that was available in 2011 on the possible mass of the Higgs boson. So the vertical axis is the chi-squared function, which contains contributions from precision electroweak measurements and from the absence of the Higgs boson at LEP, the gray shaded region on the left, and the tevatron, the gray shaded region around 160, 170 GeV in the middle. And the GFITR collaboration said, well, on the basis of this combined fit, our preferred range for the Higgs mass is 125 plus or minus 10 GeV. So they got the central value right, and now experiments have measured the Higgs mass with a precision almost 100 times better. Next slide, please. So we do not want to encourage big experimental searches for the Higgs boson. But as you've heard from Marumi, the LHC got built, and it's a fantastic technical achievement. And also, of course, the experiments are fantastic technical achievements also. Next slide, please. So 10 years ago, plus 2 days, we had the Higgs announcement seminar at CERN. Actually, of course, at that stage, it wasn't a Higgs announcement seminar. It was an announcement of the discovery of a new boson. It took some time to satisfy everybody that this was indeed the Higgs boson. So this picture I like because it shows Peter Higgs on the right, meeting Francois Englert in the middle for the first time. This is 48 years after they proposed their theory. And during all that time, they had never met, which I find incredible, the way that theorists travel around and bump into each other at conferences all the time. But somehow Francois and Peter had not met. And the other reason why I like this picture is because it shows Fabiola Gianotti, who presented the results on behalf of ATLAS that day, and of course has now become the Director General of CERN. And that all goes to prove that we don't have a glass ceiling in particle physics. Next slide. So on the 4th of July, 2012, a new particle was discovered. And it was discovered in searches for the Higgs boson. But was it possible that it was an imposter? And I compare the situation to when you're doing a jigsaw puzzle and there's a piece that's been missing for 48 years. Eventually you find a bent piece of cardboard with the picture rubbed off in the back of the sofa. Is this the missing piece? Does it have the right shape? Does it have the right size to fit into the standard model? Next slide. So Moromi has already taken you through some of the fantastic measurements made at the LHC. He's talked a lot about measurements of the Higgs in various different channels, various different production modes. But of course, there's many other measurements as well of different final states in the standard model involving vector bosons, top quarks, jets, and so on. And I think they also play an important role for the future, which I'll come back to in just a moment. Next slide, please. So this is a compilation by CMS of their results that illustrates that the couplings of the Higgs boson are proportional to the masses of other particles. So the masses of other particles shown along the horizontal scale. The diagonal dashed line shows you the standard model prediction for the couplings. You see that all those that have been measured sit on that line. And that was my then PhD student, Tivong Yu, and I wrote in one of our papers that this new particle walks and quacks like a Higgs boson. Amazingly, I think that phrase actually appeared in a journal. Next slide, please. So 2013, the Nobel Prize Committee awarded the prize to Peter Higgs and Francois Englert. And in their citation, they wrote, "Today, we believe that beyond any reasonable doubt, it is a Higgs boson." And Tivong and Yu and I were very proud because that quotation was taken from our paper. Actually, it was taken from the preprint version of our paper. But when we sent our paper to the journal, the referee said, "Beyond any reasonable doubt is not a scientific judgment. You're going to have to take that phrase out." So that phrase was good enough for the Nobel Academy, but not good enough for the journal. Next slide, please. So you might say at this stage, well, okay, the discovery of the Higgs boson completed the standard model. What else is there left to do? Maybe we just stop doing particle physics. But I would respond to that with a quotation from a poem by T.S. Eliot. "To make an end is to make a beginning. The end is where we start from." And that's very much my attitude. The Higgs boson discovery completes the standard model, but that provides us with a solid basis for our next studies in particle physics. Next slide. And in fact, although the Higgs solves a massive problem, it is extremely puzzling and raises many more problems. What's the pattern of Yukawa couplings of the Higgs? What explains the magnitude and the sign of that mass term mu? The quartic coupling, if you normalize it, seems to go negative, which raises an issue of the stability of the electroweak vacuum. And of course, there's the possibility of a constant term in the potential, or cosmological constant. And there could be additional higher order, high dimensional interactions, which I'll return to in a couple of minutes. Next slide, please. So this problem of that mass term mu led to a lot of discussion as to whether the Higgs boson was elementary or whether it might be composite. If it's elementary, you have quadratic divergences when you try to calculate corrections to the mass, and it was proposed that those be cancelled out by postulating low energy supersymmetry. So far, not seen. Moromi has already discussed constraints on the magnitudes of the Higgs couplings, which tend to disfavor the idea that it's a new strongly interacting composite particle. Next slide. Now, what about this issue of the sign of the quartic coupling and the possible instability of the electroweak vacuum? So here we have a plane of the Higgs mass on the horizontal axis, the top mass on the vertical axis. There's a green region in the bottom right-hand corner where the electroweak vacuum is stable. There's a red region in the top left where it's unstable, and in between there's a metastable region. And at the 1 sigma level, the measurements of M Higgs and M top given in the particle data group seem to indicate that we're in that metastable region. But don't worry too much. I mean, the lifetime of the vacuum would be very much longer than the age of the universe so far. And I'm sure that climate change or Putin would get rid of us before the collapse of the electroweak vacuum. Next slide. So how do we go further in answering these and other questions? So I particularly am in favor of looking beyond the standard model with effective field theory. And to motivate that, I have another quotation, this time by the Chinese strategist Sun Tzu. The direct method may be used, look for new particles, but indirect methods, look for their indirect effects, will be needed in order to secure victory. The direct and the indirect lead on to each other in turn. It's like moving in a circle. So he could have been talking about LEP and the LHC. He could be talking about a possible future circular collider. Next slide. So how does one look indirectly? So effective field theories suggest that in addition to the dimension 4 interactions present in the standard model, there might be additional higher order interactions. And, the study of such things has a long and glorious history. For example, in the 1930s, Fermi proposed his 4-fermion theory of the weak force. That was presumably due to the exchanges of massive particles. When it was established that the Fermi theory had the V-A current form, that led us to think about gauge theories with massive vector bosons, of course, motivating the mass generation mechanism of Englert-Brout and Higgs. And one could also make arguments that effective field theories are also key in leading us towards QCD, but I won't discuss that here. Next slide, please. So I think the standard model effective field theory, where we write out interactions of dimension 6 and potentially higher between standard model particles, these higher order interactions could be due to the exchanges of heavier particles. The analysis of those interactions could provide us with hints about what might lie at energy scales beyond the standard model. And I think they're the most efficient way to extract the largest amounts of information from the LHC and other experiments. Next slide. So, together with May Madigan, Kim Masuvi, Veronica Sands, and Tirong Yu, we're one of the groups that has analyzed the data available from the LHC and other experiments in terms of standard model effective field theory using dimension 6 operators. And as you can see here, I think you really want to do a global analysis where you combine electroweak precision observables, Higgs observables, top observables, and so on. Next slide, please. So here are just a few plots. I won't go into the details of them. There's no evidence from this analysis of any deviation from the standard model. None of these operators looks like it has a significantly non-zero coefficient. So there's no hint here of physics beyond the standard model. Next slide. But as Marumi has reminded you, a couple of months ago, CDF announced a new, very precise measurement of the mass of the W, which is shown here in red, and it's somewhat in tension with the previous measurements, and it's certainly in tension with the standard model prediction. So what sort of new physics could conceivably be responsible for that effect if it turns out to be real? Next slide. So as I said, I think you need to analyze in a global fit to all higher dimensional operators. And this is something that we did again, following the Fermilab measurement in a paper together with Emanuele Bagnaski. If you go to the next slide, you see that indeed there are some operators which could help explain the mass of the W if they had non-zero coefficients. Any one of these four operators could help reconcile the W mass measurement with other standard model measurements. Next slide. So could those operators be generated by some single field extension of the standard model? Might it have spin zero? Might it be vector? Might it be some additional fermion field? Next slide. So we identified 5 possible single field extensions of the standard model that could help fit the mass of the W boson, particles weighing the TeV range, which masses that would be consistent with the SNEFT approximation that we made in producing this plot. And some of these massive particles could be produced, could be detected at the LHC. Final slide, please. So I've taken you through a sort of a Higgstorical summary of how the idea of Peter Higgs, François Englert, and Robert Brout went from speculation to hypothesis to theory to experimental searches to experimental discoveries to becoming building blocks of our understanding of nature and possibly helping us look for new physics beyond the standard model. And maybe now with the W mass and other anomalies, it's the time to start repeating this Higgs story. Thank you.
Thank you very much, John. Thank you. So now we have time for questions. I see already one, so let me try to unmute you. Can
you hear me?
Yes, we can, please.
Thank you, John, for this historical perspective. There was a ghost at your feast called Susie, whom you've been desperately seeking since 1985. Do you still entertain hopes for her?
Well, no, Susie is the love of my life. My physics life, I hasten to say. And she has been, in fact, since 1979, more or less. And I must admit that I've had occasional dalliances with other theories of physics beyond the standard model, but I tend to return to Susie from time to time. And I think that, for example, if the anomaly in the anomalous magnetic moment of the muon turns out to be right, then a very natural explanation for that would be light muon and light neutralino, which would have escaped detection at the LHC. And supersymmetry could also make a contribution to resolving the anomaly in the mass of the W. So the answer to your question, David, is I haven't given up hope that maybe my love of Susie may yet be returned.
Thank you.
Okay, there is another question from Samdatta, so let me try to unmute you, please.
Yeah, so my question is, what scenario do you think is the most plausible that is now coming up for the beyond standard model physics?
Well, I'm going to have to quote what Peter Higgs said when he was asked the same question in a video that he recorded for the 10th anniversary meeting at CERN 2 days ago. And his sage answer to your question was, I don't know. I've told you what my favorite theory is, but and it does so many wonderful things. I think it would be remiss of nature not to have exploited supersymmetry. But no, nature is much wiser than I.
So maybe a comment on this it could be that for the first time, we have a theory which can be extrapolated to extremely high energies. And this is really something very new, right? So that's maybe why, one of the reasons why situation is very open.
Yeah, and I think the theoretical community, now, if I was going to be unkind, I think we all know, like chickens running around with our heads chopped off. We don't know which way to go. We can't see which way to go. Which is actually a very exciting and positive stage, and I think it provides lots of opportunities for the younger theorists. So we older theorists may say, "Ah, well, no, we still love Susie," but it's the younger guys, I think, who are going to find the answer.
Okay, so there is another question from Harnard. So let me unmute you, please.
Okay, just historically, you mentioned Nambu's contribution to the idea, and I think you mentioned Phil Anderson in passing also, but didn't Phil Anderson actually publish a paper back in 1962 in which he explained that the Goldstone mechanism can be circumvented in a non-abelian gauge theory with spontaneous symmetry breaking?
Well, I think he only ever discussed the abelian case, and as far as I'm aware, he only ever discussed a non-relativistic case. And as I mentioned, there was a lot of discussion about the generalization to a fully relativistic case, which I don't want to go into in great detail here. And in particular, there was this paper by Gilbert, which said it was impossible to generalize the non-relativistic case to the relativistic case, and that was what actually triggered Peter Higgs to say it is possible.
Well, I may be mistaken, but I think that the PhysRev 1963 paper did suggest it for Yang-Mills, not just for abelian.
News to me.
And I think it was acknowledged by Peter Higgs.
Again, news to me.
Okay.
Okay, we'll have to go back and read all the papers. So thanks, John. Thanks again. I don't see any more questions. So I think it's time to take a break.